Hello everyone and welcome to another AP Computer Science video. Today we're going to focus on creating conversions between numeric data types, particularly int and double and int, and then we will move on to creating random numbers. Both these are pretty powerful tools, particularly when used together to make random numbers, whether they're integers or double values. So I'm going to make a new class by right-clicking on Basics, the package, New Java class. We'll call this class Casting and Randoms. And so I'm going to go ahead and toss out my comments. I'm going to make my main class, my main function, public static void main string bracket args. Here we are. So we're going to start with casting. What is it to cast something? And it means to convert from one data type to another. And right now we're going to focus on primitive data type casting, and particularly focus on numeric type to numeric type, because this is one of the more common uses. You can cast from non-primitive to non-primitive types, and there's occasions where you can even go from a primitive to a non-primitive, and vice versa. But in general, the most common types of casting, at least in initial programming in Java, is from one numeric data type to another. So let's go ahead and put some notes, right? A cast is a conversion between data types in Java, right? The syntax for a cast is the data type wrapped in a set of parentheses. So parenthesis, data type, parenthesis, and then value. So what we're saying here is, and again, this is usually on the right side of an assignment or in a mathematical expression. This is not necessarily a semicolon, but generally the conversion is we're converting this value into this data type. And so we'll see some examples, and we'll point out some things about, one, its precedence, and two, its associativity. So let's do a small example. And this is one, again, some of these examples may seem very arbitrary because they're just proof of the actual mechanisms, and then we'll see when we get to randoms in particular a real usage, a meaningful usage of our data type. So here we go. We're going to go ahead and try. Let's make an integer variable, and so we'll call it num. And again, we know, according to the rules we've learned so far, that an integer variable, an int variable, should only hold an int value, or a value of another data type that can be converted without losing data, right? That's an implicit cast. I mentioned these words before, so now we're being very outright. So let's go ahead and write that. An implicit cast, a cast by the computer, so it's performed by the computer automatically, right? And we'll say it only occurs when there will be no loss of data. So for example, we haven't done it yet, but I think we have in a previous video. We've set a literal integer and stored it or assigned it to a double variable. So if the rule was the thing on the right of the assignment must match the type of the thing on the left, then that wouldn't work. But because of an implicit cast, an integer like 7 can be converted to 7.0 with no loss of data. So therefore, that implicit cast to a double could occur. An explicit cast is intentional. So in particular, we cast whether or not we lose data that is on the programmer to make the decision. We're kind of forcing the hand of the compiler and the computer. And often it causes truncation. Particularly when we're casting to ints, we are going to lose data. And that's okay. If we choose to write it out explicitly, the intention is we are okay with losing data. The computer won't do it unless we force its hand. And that's the main difference. So here's an outright example. So I might put 7.5. And we know this will fail because the literal 7.5 is of type double. You cannot store double in an int because it does not fit, right? It's too large. It's not the same data type. And so it says incompatible types. Possible lossy conversions. Look, if I converted it without your permission, I would cause a loss of data, and that's not okay, so I'm not going to do it. I'm instead going to warn you or complain to you, and you need to make a decision, either correct the literal or cast. And so how are we going to cast? I mentioned we put the data type we want to convert to or cast to in parentheses to the left of the value. So in our case, we're going to say int. And now notice there's no error. So some things to note, first and foremost, is that the associativity of this cast is right associative. It looks from right to left. It does not look, there's nothing to the left of it, so it doesn't look that way. It only looks to the right and converts to the right. So that's important. That's one thing we need to recognize. The second thing is the precedence, and we can't see it here, but we'll in the next example where the precedence happens to be. So I'll give me one moment and we'll try that out. But first we should recognize that the conversion is from double converted to an int. A truncation occurs, so the value that's stored is not 7.5 but 7, because truncation is not rounding, it just throws away the decimal, and then the answer 7 is stored. We can prove it by printing the variable value. So println num, and if I run it, we should see only 7 as our answer. So we have intentionally sacrificed the decimal portion to cast and continue our program. So again, right associative. So let's go ahead and put out that note. Casting is right. Okay, so now let's do another example. We'll say num is equal to 7.5 times 10. And so here we go. So the question will be, before I print this, and I'm going to do that, but I want to give you a moment to think about it, what would the answer we get be? There are essentially two possible answers, and it depends on the precedence of the cast against the multiplication. Who is more important, the multiplication or the cast? And I'll say is, there's no clue that gives away which one's more important. That's the kind of disadvantage here, that I would not expect you to know the answer just by looking at it. The reality is you need to understand the language's rules to know it. So what are the two possible answers? If the cast happened first, before the multiplication, we would get 7.5 cast to an int, which would be 7, and then we'd multiply by 10, which would give us 70. That's one possible answer if the cast is more important. If it wasn't more important, then we would get 7.5 times 10, which is 75.0. 75.0 cast to an int would be 75. So if we get 70, then the cast is more important. If we get 75, then the multiplication is more important. So let's see which one it is. 70. So the cast has a higher precedence than the multiplication. So now let's go real back, and I'm going to go really quickly to my my arithmetic page and copy this rules of associativity, precedence that we've done so far, and we'll come back here and I'll paste this back at the top. Right? Because we're going to adjust this list. And so now we need to stick this in somewhere. So now I know for sure it's still weaker than parentheses. Parentheses is basically always number 1. The real question, the real question is, we know it beats this one, and now does it beat this one, and does it beat this one? Where does it belong? Does it belong above number 2? Should it be number 2? Does it belong between 2 and 3? Does it belong after 3? So let's figure that out. So let's make this. And unfortunately, this might not actually even work out as being clear, because if it's before the negation, then we would cast 7.5, which would be 7, and then we would negate it, which would be negative 7, and then we'd multiply by 10. But similarly, if it was after negation, then we would just cast negative 7.5, which we would still get negative 7, and then the multiplication would occur. So whether it's actually better, or more important than the unary operators is not necessarily clear just from this example. We might have to work with something a little bit more complex. But I'll say for now, just to make it easier, it is not as important as the negation. The negation is right associative, so it will go first, and then the cast is also right associative, but in this example you will see that it must happen after the negation. Right? So it's going to fall under the negation, but the question is, and if that's the case, that must imply that it's also less important than function evaluation. But I'll give a more explicit example of why that's the case. So again, in this example, we should expect to get negative 70, and there it is, right? And in fact, it still does not really 100% clarify that the unary operator is more important or less important, because either way you would get the same answer. But now when it comes to function evaluation, this is the one that's really distinctive. Let's try this. Num is equal to, we'll cast to an int, and we'll do something like math.pow 2. Actually, no, let's do square root. Let's do square root, math.pow, square root of 2, right? And it will do times 10. So if we look at what the square root of 2 is, that's some decimal number, and so we have to ask ourselves which is going to happen first. So before we do this, let's go ahead and just get the square root of 2. And I don't necessarily know it off the top of my head, but if we were to run our calc and do 2 and then do square root, where's my square root symbol? That's 1.414 and so on. So 1.4. So if we did 1.4 times 10 and we didn't do the cast, we would get 14 point something. So let's go ahead and see that just real quick to make sure. So I'll cut it. Oh, this has to be a double. So let's make this a double temporarily. I'll just call it n. Oh, I missed the e. One more time. Oh, I didn't print it, of course. So let's do system.out.println n. This is just a kind of proof, so I'm not going to keep this. There it is, 14. It's this thing with the decimal moved over, 14.14 and so on. And so now, if I go back to how this was, if I say num, I force the cast, and I print it, we have to ask us what's more important, the function evaluation or the cast? And I don't think that we have to really think about it too hard, because if you think about it, how could you cast a number that is the answer that's without already having the answer? We need to know that it's 1.414 or whatever before we can cast it. Like you cannot cast something that you don't know. So the function must be evaluated before the cast can occur. So that officially puts us where the cast is less important than function evaluations, and we'll say for now that it is less important than unary operators. So we'll say cast, right? Casting, and we'll say right, and it will also say that it's right associative. And so now we recognize that we have parentheses, then we evaluate functions, then we evaluate unary operators, then we evaluate a cast, and then we do arithmetic, and then we do assignment. So if I run this, we get 10, because math square root of 2 is 1.414. 1 point whatever, cast to an int is 1. 1 times 10 is 10. So that's how we get 10. Now if I did this, our parentheses might change this. Now we would get 14 point something, 14.14 I believe, and then we would cast to an int and we should get positive 14. We're forcing the reordering, and there it is, positive 14. Right? So casting is pretty powerful, but if we want it to happen before or after arithmetic, we must use parentheses. It's going to beat out any arithmetic, multiplication, division, modulus, addition, subtraction. So this is important, and we'll use this soon enough with our random numbers, and it becomes an important concept. Right? So depending on where we have that, we can establish our cast. So this is casting to an int. That's okay, but we can also cast to double. And so, for example, I might do something like this. Double answer is equal to, and I'll just do a complex formula, and let's try something like let's do here we go. So now we have to kind of figure out what our order of operations is and then establish the answer, and then we can print it out. I'm not going to print it out just yet, so take a moment to do the arithmetic and figure out what the value is. So if you want to pause the video, you can pause the video. And so, order of operations, parentheses first. The outside parentheses essentially don't change anything. So the next thing that occurs is casting, because all that's left is the cast, the division, the subtraction, the modulus, the addition, the division. So the first thing that's cast is the cast. It is right associative, so it looks immediately to the right. So we get 4 cast to 4.0 because it is a double. 4.0 divided by 5 is 0.8, 0.8, 80%, right? So 0.8. So we're left with, and I'm going to go ahead and put just a note here real quick. This part right here is 0.8. And then now what's left is the next thing is 15 mod 3. 15 mod 3 is 3 goes into 15 5 times with a remainder of 0 because the modulus is the remainder. And then 37 divided by 5. 5 goes into 37 7 times because 7 times 5 would be 35. And then it would be some change, but we ignore it because both are integers. So we get 7. So we end up with 0.8 minus 0 plus 7. So 7.8. So let's see if that's the answer that we get. Maybe I'm wrong. But there it is, 7.8. So now the question is, if I didn't do the cast, what would my answer be? Is it going to change? And this is why the cast is important, because it can change the value of a mathematical expression. What changes here? Suddenly, this division, 4 divided by 5, is 0.8, but as an integer, which is truncated, which is 0. So I end up with 0 minus 0 plus 7. So I should get 7. 0.0, because 7 as an int is implicitly cast to a double when it's stored in a double variable because there's no loss of data. So we end up with 7.0 as our answer. Now what happens if we did a cast here? Does it have an impact? Right? And the answer is yes. Because 4 divided by 5 is 0, because both are ints. Modulus is still 0 because 3 goes into 15 evenly. And now it's not 37 as an int divided by 5, it's 37.5. So 5 goes into 37, 7 point, and we drop the 2, 7.4, I think. So let's see if it's 7.4. Maybe I'm wrong. There it is, 7.4. Right? Because the cast happens first. Now, if we do this, wrap the division in parentheses. Does the cast have an impact? And it's going to do something, but is it going to change our answer? So here we go. Same order of operations. The first thing we do is parentheses. The outer ones do nothing. This is the next set of parentheses. 37 divided by 5. An int divided by an int. And 37 divided by an int is just 7 flat. So, and then the 7 flat is cast to a double, which is 7.0. Then our division occurs. Our division is going to be 0 because an int divided by an int is 0. And then our modulus is 0. So we end up getting 0 minus 0 plus 7.0. We should get back to 7.0 as an answer. So the cast absolutely has an impact, but because of the order of operations, it may only have an impact in terms of converting it to a double and putting a 0.0. So essentially, in this case, this double is not helpful because this conversion would have occurred anyway because of the implicit cast, because of the initialization or the assignment to the variable. So when you use it, it's about intentionality. What are you trying to convert? Is it safe to convert? And I'll mention again, these are kind of arbitrary examples because I'm using literals. This would be much more important to force casts to doubles or ints if we were purely using variables. If we didn't know the values, then but I wanted to make sure I kept the decimal, then I would make sure I would force one to be a double. And if I couldn't change the variable types, which is a real possibility if it's not necessarily all your code, or if the variables are read from somewhere that's outside of your control, then we could at least force it to be a decimal value by converting one of them to a double with a explicit cast. Right? So again, I mentioned we're going to see some casts as a more practical use in a moment when we do our random numbers. Okay, so again, could we cast from one type to another type? Sure. Could we cast from long to short? Absolutely. Could we cast from double to long? Absolutely. It's just a matter of being careful about where the variables are stored and the same rules being applied. What do you expect to happen when you do your conversions? Okay, so I'm going to move on to the new topic, random numbers. And random numbers are very important, and casting does play a role when it comes to getting whole random numbers. But we're going to start off simple. So there are actually very modern ways to do randomness. Randomness is an important aspect of many systems. Video games in particular, entertainment uses randomness to make things interesting consistently. Most people don't enjoy games that inevitably repeat themselves, right? So if at a certain point you know the pattern, humans are good at spotting patterns, and so if eventually you spot the pattern, you might feel great because you win, but eventually it becomes boring because there's no uniqueness to it. There's no randomness. So games often use random. If you have games that have loot systems, so you get some coins or you get some points or some special item randomly, that's an impact on the game. Security also has a real kind of tie to randomness. True randomness in a computer is unfortunately not possible. And so a system that needs real randomness, can we really trust the computer? And the answer is, generally speaking, if we want true randomness, the answer is no. We get the next best thing, pseudo-randomness. Pseudo meaning not real or fake. So typically a pseudonym is like a fake name for an author. A pseudo-random number means a number that's not really random, but generally speaking is good enough to fool most human beings. And so we're going to learn the original kind of classic approach to randomness in Java, mainly because it's on the AP exam. They think it's important to know the general premise of it, and that's good, though it is not necessarily the best or most modern approach. And so I'll point that out, that if you Google how to use random numbers in Java, you'll probably find a better way than we're going to do. You're going to use the random class, and there's going to be some special functionalities, and they're great, but we need to know the classic style just as kind of being comfortable with arithmetic and conversion and that random command. The random function is a function of the math one, and we might have seen it as we were using our math library. So random, Math.random. Actually, I'll be more specific. I'll say returns a random double between 0 and 1. And I'm going to use interval notation, and hopefully you remember from your math interval notation where we put a bracket on the lower bound of our interval, and that means inclusive, and if we use a parentheses, we mean not inclusive. So as an example, this is saying from 0 to 1, not including 1, or in interval we would say 0, 1 parentheses. So we're saying we include 0 as a possibility, but 1 is not inclusive. So if we were being accurate, the closest we could get to 1 would be 0.9 repeating to about 17 decimal places. That's the biggest number we could get. We would never get 1 as an option. So that's a very limited range, so we're going to have to do some work to get to a more effective range if that's our goal. So let's go ahead and just do an example. We'll say double rand is equal to Math.random. And if I just do that and I print it out, system.out.println, and I run this, there's my random number, 0.7635 and so on. I'm going to run it again. So every time we should get potentially different numbers. That was pretty close to 1, but it wasn't 1. Something else we want to point out. Math.random aims to generate numbers in a uniformly distributed pattern. It means that it hopes that all numbers are equally likely to be generated. That's important because if it wasn't, then you could maybe see a pattern. And so if you're not comfortable or don't have experience with statistics, this is okay. Uniform distribution is essentially a straight line. It means that every number in the range is possible at an equal likelihood. If I gave an example of saying, well, actually, maybe it was normally distributed, hopefully you all remember the normal distribution is kind of the bell curve, where there's a big bump in the middle, then we could say that the math, if it was a normal distribution, then we would say that numbers closer to the ends of the ranges are much less likely than numbers in the middle. But the people that designed this function, random, aim to be uniformly distributed, not anything else. And that's kind of like a matter of fairness. Now, is it really random? The answer is no, it is pseudo-random. So if we had enough detail, if we had access to the source code, and if we studied it enough, it's possible that we could come up with a system that we would know the next random number. But it's very difficult, and it's unlikely. And in more secure systems and better random distributions and better random algorithms, it's essentially impossible to know without having some real inside information. And that's a good thing. And so in our case, it essentially is good enough for most people's uses. But I will mention that most professionals would agree that if you need true randomness or close to true randomness that's secure and consistent, this is not how you would do it. You would find a better way. There are many different libraries designed for security and cryptography and things like that. They're not necessarily going to be using Math.random. So this is good for now. Let's try the next step. Let's try to pick a range that's not so small from 0 to 1, but something a little bit better. So let's say we want to create a new range. And I'm going to go ahead and put target range instead of from 0 to 1, not including 1, I wanted something like 0 to 10, not including 10. So I could get 0 as a possibility, 2.159, 3.5, 7.7, up to 9.999, up to 9 repeating up to 16 significant figures. So almost 10, but not 10. How would I go about doing this? So I do want decimal values, and so I'm just going to put these as decimal. And so how would we do this? I would say rand is equal to, and so let's think for a moment. I'm going to pause and give you an opportunity. And again, you can pause the video. Think about what math we could do to this random number between 0 and 1 that would adjust it. And if you look at this number, what could we do to make it a number between 0 and 10, but not including 10? So if you've thought about it, then hopefully we can agree that a solution like Math.random times 10 would be a solution. Why times 10? So what I'll say is, in general, if you're unsure of what the range of your formula is going to be, explicitly try out both the upper and lower bound. Upper bound being the highest number possible and the lower bound being the lowest number possible. How do we do this? We pretend that random gives us a particular number. For the lower bound, we say random gives us the smallest possible number, which is 0. For the upper bound, we'd say random gives us the biggest possible number, 0.999 repeating. So let's try it. If random gave us 0, what would the overall lower bound be? It would be 0.0 times 10, which is 0. That's the lower bound that I wanted. So the lower bound seems to match for this formula. Let's see if we can get 9.99 repeating. And if that's the case for the upper bound, then we've done what we wanted. What's the largest number that random could give us? It could give us 0.99 repeating. If we multiply 0.99 repeating times 10, we would get 9.999 repeating. And then we would store that variable. And so that seems to work out. That's the upper bound that I wanted, 9.99 repeating. Now, could I ever get 10? I hope that you're confident that we could never get 10, because essentially what's happening is if this gives us 0.99 repeating and multiplying it by 10 shifts the decimal point over, we're going to get 9.9 something. We're never going to get 10. If it gave us 1, then we would multiply by 10 and get 10. But since it never gives us 1, we will also never get 10 as an answer. And that's a good choice. So this is a formula that guarantees that. And again, I can go ahead and print it, and we'll do that just real quick, just to kind of see some outputs of it. I'll go ahead and copy this line because we might use it again and again. So we can run it. And there it is, 2.44, 6.32, 8.73, and so on. So we can continually get numbers between 0. Now again, I'll point out that running it 20 times, 100 times, 1,000 times is not a definitive proof of this correctness. But it's as long as we don't see anything blatantly wrong after a couple, then we're probably in good shape. It's a good sense of what's happening. So let's try another number. Let's try another range, something like, let's say 0 to 23, not including 23, and I want it to be a decimal as well. So again, I'll give you a moment, pause the video, think about what you would get to make this happen. So we'll say math.random times 23. Because again, the lower bound, if random gave us 0, would be 0 times 23, which is 0. That would satisfy the first part. Our upper bound would be 23, but not really, almost 23, 22.99 repeating. If this gave us 0.9 repeating, what's 0.9 repeating times 23? It is 22.9 repeating. And that would be the upper limit that we wanted. We don't want 23, we want almost 23. So, if we want to just get our range from 0 to some larger number, then all we must do is multiply that number. And that's a pretty convenient thing to do. So let's go ahead and try something a little bit more complicated. Let's say our range no longer begins at 0, but begins at some other number. Let's say if we want it from 5 to 10, not including 10, and we still wanted a decimal number. What would we do here? So I hope you thought about it. We can say math.random. And now what happens is, if we want to adjust the upper bound, we saw that we could multiply by a number. If we want to adjust the lower bound, we can add or subtract a number. but by doing so, we also affect the upper bound. Multiplication simply affects the upper bound. Addition affects both the lower and upper. So if we're going to adjust the upper bound by multiplying and adjust it by adding, then when we do our multiplication, it should be offset by whatever we added or offset by whatever we subtracted. So in this example, we should try multiplying not by 10, but by 5, and then adding 5. So if we're not sure that this works, let's prove it. Again, we'll test on the lower bound with random being 0, and we'll test on the upper bound with random being 0.9 repeating. So if random is 0, 0 times 5 is 0, 0 plus 5 is 5. That is our lower bound, what we wanted, so it works at least for the lower bound. How about the upper bound? It should be 9.9 repeating, and that's hopefully what we'll get. So what would 0.9 repeating multiplied by 5 be? That would be 4.9 repeating. 4.9 repeating plus 5 is 9.9 repeating. So it never gets to 10. It gets close, but it never gets to 10. So this is the range that we want. And so hopefully we see that this adjustment is that the multiplication adjusts the upper bound, but then so does the addition. So we have to kind of gracefully readjust the upper bound. And the addition by itself simply affects the lower bound. So let's try one more version of the same idea. So let's try something a little bit more exotic. We'll say range is from, let's say, 13 to 29, not including 29. And we still want decimal numbers. So we would say rand is equal to, I'm going to give you a chance to pause and think about it, and then we'll try it. So we'll say Math.random. And now again, the multiplication, if I just put 29, that might be correct, but because we're also going to adjust the lower bound, we need to unadjust or backpedal a bit on our upper bound. So we're going to say 29 minus 13, that is 16. So we're going to multiply by 16, and then we're going to add 13. So let's see if that actually works. Lower bound, 0 times 16 is 0. 0 plus 13 is 13. Looks good. Upper bound, Math.random gives us 0.9 repeating. 0.9 repeating times 16 is 15.9 repeating. 15.9 repeating plus 13 is 28.9 repeating, so almost 29, but not 29. This looks good to me. So I hope that we see this kind of pattern, and I'll ask you, could you generate a generic formula that uses variables instead of these exact numbers? And I'm betting that you could if you thought about it a little bit and maybe made variables, called them upper and lower, or high and low, or top and bottom, and then do only variable math, don't show any exact numbers. That would be a useful practice example to do, and hopefully you could find one. I'm also going to try, and I'll do that one right now, but let's also try considering another scenario, because we've done from a positive number to a positive number, but what about a negative number to a positive number? Could that range also be generated with randoms? And the answer is probably. But before we do it, I'm going to instead move on, because decimals is great, but I want to kind of make this a little more interesting and say, could we get random ranges of numbers with only integer values? That's the next thing we're going to try. I'm going to go ahead and end this video, and I'll continue in another video with the integer version of random numbers. I'll see you in that next video.